Good day, everybody. So let's take a look at some select topics from the introduction to organic chemistry. Today we're going to concentrate on largely two topics. That's the nomenclature of alkenes and alkynes. We're going to take a look at some examples. So we're not potentially going to go through all the possible rules, right? Because this is something that is chiefly either in the textbooks or some sort of presentation slides. But today let's just take a look at some examples. So which is what is supposed to be happening at practice sessions, right? So then we're going to switch gears towards reactions. We have seen some reaction types already that pertain to unsaturated compounds, namely alkenes chiefly, alkynes as well. So, and then we're going to take a look at some rule, or one of the rules that governs how certain addition reactions take place. If you are to choose where the particular atoms will go, and where they will go will influence the structure of the product you are going to get. So yeah, this is kind of like the overall considerations that we need to keep in mind for today. And now, without further stoppages, let's go ahead and continue with our problem number one, right? So which will be about nomenclature. So I'm just going to draw some structures and then we'll be assigning names to them according to like the rules we have had so far. So the first one will look like this. So we'll have the methyl, and then as you draw the structures, right, sometimes you can kind of like pronounce the names of the building blocks, such as like a methyl here, right? So then we'll have like methylene. So then we'll have the here the tertiary carbon, right? So that is having no hydrogens, but it still has 4 bonds total. So then we have here the methine and the methyl again. So, and then on the bottom here, branching out, we'll have CH2, CH3, okay? So now let's take a look at the longest chain that we can see here, right? So this compound is an alkene, so because it has this one double bond, so we need to make sure that we include both atoms that contain double bond into the longest chain that we can find out. So, and then by the look of that, so the longest chain will be this one, right? So it contains 5 carbons and also contains both carbons that constitute the double bond. Okay, so then if we look at this chain here, which I'm trying to trace with a pencil symbol, 1, 2, 3, 4, 5, it also contains 5 carbons. But in this situation, the only 1 carbon from the double bond formation will be included into this chain, and then this carbon, like sp2 hybridized one, will be kind of excluded from the chain. So this situation does not pan out. Okay, so that's why we're going to choose this one. Okay, so we have 5 carbons in a row, right? So in that case, we can start drawing already, or like dropping the parts of the name. So 5 carbons in the chain. So then the name will be having the root of pent, right? Which stems from pentane. That is kind of like the alkane, the corresponding alkane, but we're going to have the alkenes. So that's why we're going to switch from ane to ene, right? So this will be like pentene, right? Some sort of pentene with a substitution. So let's call it this way, pentene. So then let's number the chain, right? So we're going to maybe start from here, from the left end, or from the right end, as we can like observe this molecule. So we're going to start from the end that is closest to the start of the double bond, right? So if we start from here, left to right, very tempting. So we're going to be like 1, 2, 3, right? And then looks like the double bond will start at carbon number 3. So if we start from the right end, so we are going to be like this, like 1, 2, right? So, and then on carbon number 2, the double bond will start. So, which is what will get the upper hand. So if we start counting the carbons from the right end, 1, 2, 3, 4, and 5. Okay, so in this counting scenario, the double bond will start on carbon number 2 as opposed to carbon number 1, 2, 3, right? If we count left to right. So then the double bond starts at the earlier or lower numbered carbons. So, and that's good for us. So then what else? On carbon number 3, we will have, what is that called? That's called the ethyl group, right? So then let's put together the rest of the name. So yeah, basically pentene, right? So as you remember, we need to show the number before this name, right? Before pentene, part of the name. So the number will show where the double bond is located, right? So the number here before pentene will be 2. So now it's more complete as the name, because we have the position of double bond on carbon number 2. There is the double bond, right? So on carbon number 2, double bond starts, and then it finishes on carbon number 3, right? So that's the only way to like think about it. We go forward in numbering, like no backwards, not backwards when we think about how the double bond like, goes and where it finishes. So then 2 pentenes. So on carbon number 2, this is our double bond starting, and like 2 basically will pertain to this like in part, right? So pent stands for 5 carbons in the chain. Okay, good. So now finally let's add the substituent. On carbon number 3, we will have the ethyl. So let's put it this way. So 3 ethyl dash 2 pentene. Okay, that's it. 3 ethyl 2 pentene is our molecule. All right, great. So now again, just kind of like numbering, substituents, position of the double bond, right? So these are pretty much the most common things in naming we have for our considerations. So now let's move on to other cases, such as maybe another alkene here, right? So this one will be a little bit longer chain-wise, so but it's good for us. So because we are going to go through like various nomenclature items. So CH, CH2, CH3, and some tricky situations as well, so that we're going to consider. So here it is. So if you look at the longest carbon chain, so looks like it is going to be like this one here, 6 carbons. If you go this way, 1, 2, 3, 4, 5, 6, 6 carbons as well. But those 2 methyls are equivalent, right? So yeah, basically just take whatever looks the straightest. That's easier to deal with. And then they both, this chain or that chain will be the longest chains, right? So they're kind of equivalent. So now, because of those 2 methyl groups, they are equivalent. So yeah, anyway, now let's take a look at this one, right? So which is kind of like unbent, right? Horizontal. So the double bond is here on this carbon or that carbon, right? So now if we start the count goes like this: 1, 2, 3, right? So, and then the double bond will start on carbon number 3 if we count right to left. If we count left to right, 1, 2, 3, the carbon, the double bond starts also on the 3rd carbon, right? So now we need to take into account the branching. So the branching is that when you have another carbon or maybe more carbons stemming from the main chain, right? So that's what we mean by branching of the chain. So here we have the branching, right? So, and then we are going to start our count now in case double bond is in the middle or equidistant from either end of the chain. Then we are going to start the count from the end of the chain that is closest to the branching start, right? So apparently, so the left side of the chain is closer to the branching commencement than the right side of the chain. It's very far from the branching commencement point. So consequently, we'll start counting from here, from left to right. 1, 2, 3, 4, 5, 6. Okay, great. So that's our 6 carbons right here. So 6 carbons meet the what's it called? The root for this main chain will be hex it will contain the word hex or the part hex, right? So since we have the alkene, so we need to switch from ane, which would be like true about a hexane. So we need to switch to ene, and then we're going to obtain the part of the name, which is looking like hexene, right? So ene stands for the fact that you have the alkene in your case. So then let's see where the double bond starts, right? It starts on like the lower number carbon and it finishes at the higher number carbon. Basically, if you want to think about like this in general terms, it's going to be n to n plus 1, right? So number to number plus 1. So like 4 to 5, 7 to 8, things like that, right? So here, 3 to 4. If n is 3, then 4 is n plus 1. So, but anyway, so here, so the double bond starts at carbon number 3. So then basically carbon number 3 will start the double bond. Okay, 3 hexene. So on carbon number 3, the double bond starts, right? So position of the double bond kind of like signifier, right? So finally, we have one substituent here, and this one is called a methyl group, right? So, and then on carbon number 2, a methyl is located. So it's going to be 2-methyl, 2-methyl, 3-hexene. Okay, great. So these are our alkenes so far. So let's switch gears to alkynes and see what we have in stock for those guys. All right, so let's take a look. So yeah, this is going to be a branched alkyne. So CH3 here. So then C with the triple bond.
Yeah, I can do
Carbon,
that. 1 minute.
single bond, carbon.
That is Josh.
So then we'll have the ethyl group, CH2, CH3, technically, and then we'll have a couple more methyl groups attached to that kind of tertiary carbon, right? So that has no hydrogens. So yeah, a whole bunch of carbons.
What?
So then now let's take a look at what we have here.
Oh.
So this one will be an alkyne, right? And the alkyne, this is something that contains the triple bond, right? So of course we can have all other things here, so such as our branching, right? And the respective substituents, which are gonna be called methyls in this case. So that's it. That's your building blocks, right? So you have to identify the longest chain that would still contain both atoms that constitute the triple bond. So and then looks like this is going to be our candidate for the longest chain, right? About here, right? So we have, if we count 1, 2, 3, 4, 5. That's not the longest, right? So 1, 2, 3, 4, 5, not the longest as well. So, but if we go from here to there, then we'll count 6 carbons in the longest chain. So that one wins, apparently. So now, what else? So if we have the 6 carbons, so the root will be hex, right? So now we need to add the respective, like the ending of the name or the suffix, right? Which will signify the nature of this unsaturated compound, right? In this case, sorry, I need to erase that, I guess. So not to make it look like a pentavalent carbon. So if we have the triple bond in our main chain, we are going to assign the suffix of Y and E, hexine, right? Triple bond is there in the main chain. So now we are going to start numbering, right? So we can start numbering maybe from here, 1, 2, 3, right? 1, 2, 1, 2, 3, 4, 5, 6, right? So 6 carbons in a chain, right? So if you look at this end, right? Here, 1, 2. So on carbon number 2, the triple bond will start. So like 1, 2, 3, 4, 5, 6, right? So the triple bond will start on carbon number 2. If we start from this end, let's just like pretend that we don't see those numbers on the top. But if we start counting from the right end, so what will happen? Where will the double bond? Well, where will the triple bond? Sorry, commence? 1, 2, 3, 4 on the fourth carbon. That's going to be too far, right? So first of all, we need to kind of like our first line of selection, right? So from which end we are going to number the chain will pertain to the allocation of the triple bond. So the triple bond should be closest to one of the ends, right? So in this case, and then, yeah, the triple bond should get the lowest possible number. So we have a choice between assigning number 4 to where the triple bond starts, or assigning number 2 to where the triple bond starts. So in this case, the bond is clearly not equidistant from either side, from either end of the chain. So it's closer to like this left ish side of the chain. So consequently, we're going to start from left to right our count of the carbons. So the triple bond looks like will be located on carbon number 2, and we'll finish on carbon number 3, right? So we'll go from the lower number to the higher number. So to show the direction of the double bond, triple bond, sorry, we are in alkynes right now. So anyway, so carbon number 2 will contain the triple bond, right? So that's going to be the connection, but essentially between number 2 and the suffix of wine. Okay, so 2-hexane on carbon number 2, the triple bond will be located in the 6 carbon chain. Okay, so then what else? We have now substituents. It's going to be a couple of methyls on carbon number 4. So let's do it this way, right? So we need to have the methyl and 4 in the name. So since we have 2 methyls, we are going to say that we are going to have the di-methyl kind of like part to the name in here, right? So now we're going to show where those 2, so di stands for 2, by the way, that's the Greek prefix, right? So those 2 methyls are both located on carbon number 4. So according to the rules, we'll need to kind of like double the name or the number of the carbon, and it will become 4,4. 4 dimethyl.
I know. Yeah, you want it back?
4,4 dimethyl to hexane. All right, so
He was like, "That's a Susan answer." How I answered before.
technical
It's strong.
here. I'm going to mute some people. All right, so and now people are muted, so we're good to go. So 4,4 dimethyl 2-hexane is here. So anyway, just to recap, right? Carbon number 4 will contain 2 methyls. Carbon number 2 will have the start of the triple bond. So that's it. So you have your name down. So now let's take a look at a little bit more challenging case, which will still be about a, what's it called? Which will still be about an alkene with some substitution going on, right? And branching as well. So, and then also this alkene will have the, or alkyne, sorry. So this alkyne will have the triple bond in the middle, basically. So just to put things in a simple way. Sorry, I need to respond to that. All right, so all set. Friday things. So anyway, so this is not as strict as a presentation. So CH3, CH. So we have methyl, methine, CH2, right? Methylene, by the way. So then you have those tertiary carbons, right? Or they're called ternary. So that's basically like without hydrogens. So, but for now, let's just call them carbons without hydrogens, right? But they will still contain the 4 bonds. Okay, so lots of opportunities for reviewing, by the way. So, and then that's what we have here, right? So now we're going to add one more substituent, like bromine. Okay, great. So now let's take a look at the longest chain here. So it looks like this one, 6 carbons, or that one, 6 carbons. Those 2 methyls are equivalent. So yeah, we'll just kind of like use the straighter chain, right, for convenience. So now let's take a look at the position of the triple bond, right? So that's our first thing to like be concerned in terms of numbering. So it's kind of 1, 2, 3, 4, 1, 2, 3, 4. So it is in the middle, right? So or equidistant from like either end of this longest carbon chain. So then if it's equidistant, we need to look at the branching. So this is just a substituent, right? By branching, we mean typically the presence of the carbon-based branches, right? So this is not a carbon-based branch. It is just a substituent, right, on the carbon-based branch, so which is bromine. So then the branch will be represented by this guy. So the methyl, so because it contains the carbon. So consequently, so since the triple bond is equidistant from either end, we're going to start the count from the end, which is closer to the carbon-based branching, right? So which is the right end. So let's number the chain 1, 2, 3. Actually, so I made a mistake here. So 1, 2, 3, 4, right? 1, 2, 3. So yeah, either way, so from the right end, the count of the carbons will start, because the right end will give you the commencement of the triple bond on carbon number 3, whereas the left end will give you the commencement of the triple bond on carbon number 4. So yeah, that's an easier case. So the triple bond is not equidistant from both ends, right? I miscounted the carbons. So yeah, it's closer to the right end of the like main chain. Okay, anyway, so we're going on. So 1, 2, 3, 4, 5, 6, 7. Okay, 7 carbons in the main chain. Very good. So now if we have the 7 carbons in the carbon chain, so the root for this name will be hept, right? So from heptane, so which is going to be the parent alkane, if you will, but now we have the alkyne. So consequently, we're going to give it the suffix of wine, heptine, okay? Heptine will be contained will be contained on carbon number, what's that? Let me just make some adjustments. Okay, the heptine will be contained where? So, or the triple bond rather will be contained on carbon number 3. So carbon number 3 will contain the triple bond. So basically 3 will mean that you have the triple bond, which is signified by the suffix wine. You will have the triple bond commencing on carbon number 3, 3 heptine. Okay, great. So just like with alkenes, except we have a different suffix. So now, what else do we have here? So we have here also substituents, right? So essentially, so which is methyl on one hand and bromine on the other hand, right? So here it is. So we have 3 heptine, and now we need to add our substituents basically to the name. So substituents, as you remember, will be placed or sequenced alphabetically. So we have a methyl, starts with an M, bromine starts with a B. So bromine will come first, then methyl will follow, okay? So here we go. So let's put the names, or the parts rather, so such as bromo, right? So this will be the name of the bromine-based substituent right here, right? So we'll have the Br here on carbon number 6. So carbon number 2 will have the methyl. So methyl will be following the bromine, right? So just alphabetical sequence. So now let's show where the substituents such as bromo and methyl are placed on the main chain, right? So even though the numbers will be kind of like not going in the right order, right? That's okay. So the order of the substituents alphabetically, that's what matters first, right? So here we go. So carbon number 6, right? So carbon number 6 will contain bromine. So, or we can say on carbon number 6, we'll have our bromo group, right? So that's how the name of the bromine changes in this kind of like nomenclature things. So 6 bromo will be like part of the name. So then finally, so methyl is located on carbon number 2. So consequently, we'll have 2-methyl, right? So on carbon number 2, a methyl is located, so 2-methyl. So 6-bromo dashes where they are needed, so 2-methyl dash 3-heptine. So that's it. So we have our kind of like big alkyne right there. So, and that's it. So like finally we can move on now to the next problem. And in the next problems, we'll take a look at the addition reactions, right? So here we go. Let's take a look at them. So what we have seen in our past so far is kind of like a limited set of addition reactions, right? So what do we mean by that? So basically, you will have some sort of unsaturated compound. So here, normally, not here, but so far we have considered alkynes and alkenes, right? So, and then we can add some other chemicals to those. So if you think about it, so yeah, maybe you will have some sort of unsaturated compound, such as maybe, let's say, let's take a look at some kind of like random examples, so to say, right? Such as C3H6, just to illustrate the addition reaction philosophy from like one approach, plus A2, right? So it's going to be some sort of like random chemical. So A2, so it's like literally like nothing we can think of, right? So it's just like a designation so that we have a bimolecular compound, right? Or diatomic compound, right? So maybe it's going to be Br2, maybe it's going to be F2. So A stands just for some kind of atom, right? So and there are two of them in the molecule. So then what you're going to get is something like this, right? As kind of like generic result, right? So you're going to retain the atomic composition of the original organic molecule, right? C3H6 in this case. So that's going to be like a specific organic molecule. Then you add something kind of like general, right? So that contains, for example, two atoms, right? Maybe it's going to be bromine, bromine. Maybe it's going to be like fluorine, fluorine. Examples are plentiful, right? And you're going to have the general structure like that, C3H6A2 from the molecular formula point of view, right? So as you see, nothing disappeared, nothing was kind of like cut out from the organic molecule, C3H6 here, so everything was preserved. And then basically you have the addition of the two molecules. That's what the addition reactions are about. So, but then if we look a little bit further into the details, then we'll realize that those addition reactions will be kind of like associated with the breaking of the certain bonds, right, in both compounds, actually, like C3H6 and A2 in this case, and the formation of the new bonds, which will be kind of like related to the organic compound C3H6 here. So then if you look a little bit more into detail, right, so you can think about already this scaffolding approach to chemistry, and then maybe not chemistry, so only to other sciences and whatever you study, maybe some sport, language, whatever, right? So then you can see, okay, well, so what kind of bonds are going to be formed, right? So we're going to be looking at covalent bonds. So we'll typically be forming just a single, at this point, covalent bonds. So what's a covalent bond? It's like the bond which is made of like two electrons, right, contributed by like each of the like elements, each of the elements or each element that make that single covalent bond. So yeah, just again, if you think that way, so hopefully it will give you some like opportunities for reviewing, right, of things that you have learned so far. And you can potentially find some sort of like things, some topics that you need to address. Oh, I don't remember what the covalent bond is. Okay, well, let's take a look at that, talk to somebody in the literature, instructor, and so on, right? So yeah, it was just a little bit of the segues, so, but now let's get back to those, what's it called? Addition reactions, right? So now it's going to be our item 3. Here we're going to take a look at some exercises and examples of those addition reactions alongside a single rule we have seen so far. So let's take a look at hydrogenation reaction, right? So hydrogenation reaction can be applied to alkenes, for example, and here we have a particular substrate, right? Substrate, that's what we call the reactant, right? So it's like one of the synonyms in terms of the chemical terms that we can use, right? So let's take a look at the substrate like that. So here we'll be looking at the cyclic alkene, right? So that's our cycle with 5 carbons in the cycle. It's like looking like a pentagon, right? So double bond and the methyl group right here. So CH3. Let's have this combination between the skeletal and expanded or condensed structures rather. So then we're going to add H2. That's our other reagent. So then in terms of conditions, we normally have elevated temperatures, but for our intents and purposes currently, we'll just like show the catalyst because it's kind of important, right? So since without the catalyst, the reaction will be taking like excessively long amount of time, but with the catalyst, it will go faster, right? So that's the point of the catalyst. So then we're going to have here what? So we are going to have the breakage of that pi bond here, and we are going to saturate the carbons on the top and on the bottom. So as a result, we are going to have to produce a cyclic alkane, which looks like that. So that's it. So now if you count the carbons, or rather hydrogens, right? In this case, you have no hydrogen, 2 hydrogens, right? So, sorry, you have no hydrogens here, but on this carbon, you have only 1 hydrogen, right? So 1, 2, 3, 4, 4 bonds. 1, 2, 3, 4, 4 bonds. So like carbons, both here on the top and on the bottom, are tetravalent. All good. So now if we look at this, situation here. So 1, 2, 3, 4. So now the carbon here on the bottom kind of gets an extra hydrogen from the hydrogenation reaction, right? And then the carbon on the top will also get an extra hydrogen from the hydrogenation reaction. 1, 2, 3, 4. 4 bonds on the carbon. So all set. So yeah, just kind of like look into the details. Just make sure that you have like not less than 4 bonds, not more than 4 bonds on the carbon, right? So, and you only add hydrogens. So that's pretty straightforward here. Okay, so hydrogenation reaction is here. So now let's take a look at more examples. So maybe we'll have something like addition of the bromine, right? So A2, in our terms, bromine to the alkene molecule. So we go from the unsaturated molecule to the saturated molecule, which is going to be just a substituted alkane, if you think about this. So we are going to start drawing our structure, which looks like so. CH, double bond CH, CH3. So that's our double bond right here. So we're going now to add bromine 2, right? So that's our diatomic molecule, and we're going to see what happens. So in this case, leave everything else intact except only the one of those single bonds in the alkene part of the molecule. That's what you're going to be concerned with. So everything else kind of like don't touch it basically, right? So now let's redraw the part of the structure and add, literally, as the name suggests, our atoms, right, of the bromine. So I need to make some adjustments. Okay, so now here we go. So CH, so the sigma bond will stay. So as we earlier discussed. Okay, so now that bond will be broken. So let me just look at the electrons. Maybe we'll circle them a little bit. So those electrons will be forming now the new bonds. So they became separated. So you have this kind of squiggly line. Trying to make a squiggly line here, so that shows the like breakage of the bond basically. So now you have no bond between those two dotted electrons. So the bromine the bromine molecule, right, will have like 2 atoms of bromine. Each bromine atom will contribute 1 electron, right? So then we can show it right here. So bromine and bromine, 1 electron, 1 electron. Now you're going to make the covalent bonds. CBr, CBr. Okay, great. So that's your substituted like alkane, if you think about that. So that has this kind of straight chain and then the cyclic part of the alkane, but it's going to be already a saturated compound because we don't have any double bonds in this case. Okay, so now let's take a look at maybe some more examples, in which case we're going to take a look at the addition of HBr and HCl, right? So hydrohalogenation. So this is going to be our halogenation reaction because we purely add the halogen molecule, right? So Br2, that's an example of the halogen molecule. If we do the hydrohalogenation reaction, however, we are going to add H and Br. So we're going to add like two distinct atoms which were confined originally to just one molecule, right? So let's take a look at some examples. Very difficult switch. All right, so but bear with me. Okay, so let's see what we have in stock for more examples. And then in these examples coming up, we are going to recall one of the rules. So maybe it's going to be a good idea for you now to recall this rule, and it's going to be kind of like exemplified by a couple of reactions in the future. Okay, let's start with the just a linear branched alkene. So this is our 4, perhaps. So anyway, so CH3 carbon double bond, CH, CH2, CH3. All right, and another methyl right here. Okay, great. So then we are going to add HBr to that. And now, according to our considerations, we can potentially have two isomers, right? So because we can add, let's say, if I highlight, I can use a highlighter right now, highlighter, this one. Okay, so this carbon and that carbon, right? So let's call them left and right. Okay, left and right carbon. So what's going to happen? So potentially you can add HBr, right? So in either fashion. So either Br, let's say, will go to the left carbon and hydrogen will go to the right one, or bromine will go to the right carbon and hydrogen will go to the left one. So in this case, if you think about it, so you're going to potentially have two isomers, right? So depending on where the bromine atom will be located, you will have different compounds, right? From the like structural point of view, even though they will have the same exact molecular formula, right? So, but depending on where the building blocks are placed, we'll have different compounds, right? So now let's decide. So what will help us? It's going to be the Markovnikov's rule, right? Which will basically say that the hydrogen will go to the carbon from the double bond, which originally had more hydrogens, right? So in this case, you are going to consider L and R. So then apparently the R, the right carbon, will have more hydrogens than the left one. So consequently, hydrogen from HBr will continue or will be added to the rightmost carbon, and bromine will have to go to the leftmost carbon, right? So in other point of view, so we can say that the bromine atom, right, or the halogen generally will be connected to the carbon, which is more substituted. So, and then if you look at the right carbon, then the right carbon has the connection to the 1 and 2 carbons, right? So the it's kind of like double substituted, right? So if you think about it, so if you take a look at the left carbons, so the left carbon will be having the connections to 1, 2, 3 carbons. That's more substitution on the leftmost carbon. So either way, we are going to come up with the right product, right? No matter how we look at this rule. So, and the right product will contain bromine on the left carbon, more substituted carbon, right? So, and the H will be connected to the right carbon, which has more hydrogens. All right, so let's draw it this way and see what happens. So we're going to have the saturated compound at this point. So saturated compound will be formed, CH2. Well, maybe we can explicitly show the bond because why not? Okay, it's very hard to switch the tools for some reason. So our hydrogen is here on the carbon with the more hydrogens. Our bromine is here on the carbon, which is more substituted, right? So that's it. So now we have the like alkane technically here with the bromine, right, as one of the substituents, and that's it, right? So you have branched basically like alkane with the bromine as a substituent. So if you think about it. So now let's take a look at another example of this Markovnikov's rule and see what we're going to get. So we just switch substrates a little bit. So we're going to have a cyclic compound. So to diversify our adventures a little bit. So, and we're going to add HCl to that. So in this case, again, so this is our carbon, right? This is our carbon. So who has more hydrogens, right? That's going to be the carbon, which is to the right. Okay, so we have our rightmost, leftmost carbon. Okay, so the rightmost carbon will have only 2 hydrogens, not just 2 hydrogens, right? So the leftmost carbon will have like 0 hydrogens. So consequently, the hydrogen from the HCl will have to go to the rightmost carbon that contains more hydrogens. So let's keep it in mind when we draw the final molecule. Okay, so the chlorine consequently will have to go to the left carbon, which is also coincidentally more substituted. So if you think about it, the rightmost carbon is connected to only 1 carbon, right? So that's what we think about when we mean substitution, right? So, or when we say substitution. So the leftmost carbon will be connected to 1, 2, 3, 3 carbons, right? So this is a more substituted carbon. So then consequently, chlorine will have to go to the more substitute carbon, which will be the left carbon here. Okay, so chlorine is here. So now you have it, right? So let's count the bonds here. 1, 2, 3, 4. 4 bonds. So this carbon contains no hydrogens, right? 4 bonds to like other carbons or elements. So now this carbon has 1, 2, 3, 4. 4 bonds as well. So all set. We have tetravalent carbons everywhere, no pentavalent, no trivalent carbons. So everything is kind of like followed from the rules perspective. Okay, so now let's move on to, and then yeah, here it was another example of the Markovnikov's rule, by the way. So now let's move on to problem number 5. Okay, so let's take a look at what happened here. So yeah, this problem will be kind of reverse, right? So because we're going to look at the products first, and then we need to consider or come up basically with the reactants that were used in order to obtain those products, right? So that's a little bit of the challenge. Maybe, maybe not, who knows? So now let's start with our product. And then the first example will be like this. So we have the reaction arrow. So we have something here on the left side, just up to us to decide. So and then we're going to have the product like that. So CH3, CH2. That's going to be like a substituted alkane. So it will contain 2 bromines as substituents on CH3. Okay, great. So now what happened here, right? So what's going to be the substrate? So looks like we added 2 bromine molecules, right? So to the original compound. So that's what we can like think about, and then try to match it with the reactions that we have known so far, right? So 2 bromines are added. So basically, so they could be coming from the Br2, right? So the molecular bromine. So what else do we need to do, right? So like we have been looking at alkenes, alkynes, alkanes, right? So it looks like the best candidate here will be the alkene molecule, right? To get those two bromines from the molecular bromine. So let's see what we have. So looks like so our molecules rather, so of the products or sorry, reactants will be like that. So we'll have the bromine 2, but what's left over? Left over is this basically carbon stuff, right? So CH3, CH2, CH, CH2, and CH3. Let's draw it and see what we need to add in order to make this molecule proper. CH2 and another methyl. Okay, great. So we have the single bond, right? So we need to have the single bond as well here just to connect those two parts of the molecule, right? So, but then looks like we have those two bonds to the bromine atoms, okay? So the two bromine atoms came in to make the final molecule. So originally the compound that was organic compound did not have the bromine. So, but instead it had the double bond, which is broken, right? And now if we look at those two compounds in combination, right, alkene and bromine molecule, then it's going to be like nothing more than our good old bromination reaction, right? So which will result into the saturated compound, so which will be some sort of substituted alkane, right? So if we just check what happens, okay, well, so we have the alkene here, so this bond will be broken. The two bromine atoms will be connected to the electrons, which were liberated after the breakage of this pi bond. And now we're going to form two kind of like single bonds here between the carbon and bromine atoms. Okay, great. So it's our alkene bromination reaction in place. So that will lead us to this product. All right, so now let's take a look at some other examples, right? So maybe we have something like that. So, and then in this case, we're going to obtain a carbon chain, right? Basically, that contains 6 carbons in a row. So, and then it looks like that. So let's see, just a little bit more modifications to make. So that's it, right? So you have hexane right here. So 6 carbons in a chain, you're going to have the alkane. So alkane is a saturated compound. So what do you need to do to make it, right? So you can make it from an unsaturated compound, right? Unsaturated compounds such as maybe like alkyne or alkene. Let's imagine we have the alkene, right? So there could be again, so in some cases, several correct answers, right? So it doesn't kind of like necessarily have to be what I tell you, right? So, but it needs to make sense. Generally speaking, then yeah, it will be considered as a possible option, right? So then you start with like 6 carbons in a row, okay? That's your 6 carbons. So, and then we have the saturated compound as a result, right? So, but we can start with an unsaturated one. So then we can think about some kind of reactions that we have seen, right? Looks like we just need to add hydrogens to the unsaturated compound to make the saturated one, right? Nothing else is here, no halogens, no anything. So then we are going to add H2 to our original molecule, right? And the original molecule can be, for example, maybe like 1-hexene, right? So such as this one. So everything else is saturated. CH2, CH2, CH3. Okay, great. So 1-hexene is hydrogenated in this case, right? So then you are going to add hydrogen here to make CH3, and you're going to add 1 hydrogen here to make CH2, right? So, and then that way, overall, you're going to obtain your hexane molecule. So all good. So, however, what do I mean by like other correct answers? So maybe you have a double bond here, right? Maybe you have a double bond like somewhere else. So either way, the double bond will be hydrogenated, right? So it means that the pi bond will be broken. So maybe this is going to be our pi bond, it will be broken, and then it will contain, yeah, it will contain 2 electrons, right? So that will be separated. So now each electron will be connected to the hydrogen, which also bears 1 electron each, right? And then you are going to make your saturated compound with this kind of like CH3, CH2 motif out of CH2CH motif. Okay, great. So hydrogenation reaction was applied in order to make this particular saturated compound. Okay, so now finally the most challenging case. Okay, let's take a look at that. So we're going to have the again 6 carbons in a row, and then we're going to have the substitution happening right here. So let's see what we have in terms of the substituents. It's going to be chlorine. Okay, chlorine is connected now to the carbon chain. So if we think about hydrogenation, doesn't make sense, right? So if we think about chlorination, just adding of Cl2 or molecular chlorine, doesn't make sense. We only have 1 chlorine in our resultant product, right? So consequently, we're going to add HCl. That makes more sense, right? So then we're going to consider the hydrohalogenation reaction, right? So we're going to add HCl here. So HCl will be one of our reactants. The other reactant will have to contain 6 carbons in the chain and the double bond, right? So let's see what's going to happen here. So the double bond will be there. So in this case, we are going to place double bond in a particular way, right? We cannot put it here, for example, because the position of the chlorine will not be matching the position of the chlorine in the final compound, right? So that's going to be kind of like a bad choice. So just like consider what you are doing. So let's see where we can place a double bond. So what if we place a double bond here, right? So for example, like at this carbon, then in this situation, that's going to be a possibility. So because we are going to add, let's say, hydrogen here, right? And chlorine will be here on the 3rd carbon. So potentially you will make like a mixture of isomers, but it's going to be one of the possible products that you are going to obtain, right? So here, Markovnikov's rule will be kind of hard to apply because either this carbon or that carbon are kind of like equally substituted, right? So then also both of these carbons will contain 1 hydrogen, right? So neither of them will contain more hydrogen than the other carbon. So that will also not help with the Markovnikov's rule, right? So we can potentially think about how we're going to form a mixture of isomers, right? In which case you will have the 3-chlorohexane as one of the compounds, and you will have the 2-chlorohexane as another isomer compound, right? So then what else can we do? So maybe what if we place the double bond here, right, on the like in the middle? So can we make our target compound? Let's take a look at this example and see what happens. So as you see, sometimes it can become like really branchy, pun intended. So this like type of chemistry, but that's how it works. So in this situation, we are going to like add, let's say, so that's our saturated part of the chain, right? So we have here, let's erase that and just assume that this is just an alkane part of the chain. That's our alkene part of the chain, right? So we're going to add HBr or HCl rather to this alkene, right? That's going to be 3-hexane. So in this case, no matter where we are going to add the chlorine, right, from HCl molecule. So chlorine will be here or there. So we're going to have the same compound, right? So probably in terms of the purity of the final product, so this is going to be a better candidate, right, to obtain this compound. So let's go with 3-hexane. CH3, oh, sorry, that's too bad. So CH3, CH2, CH, CH, CH2, and CH3, right? 3-hexane. 3-hexane or 3-hexane. No matter where you start the count, you'll have 3-hexane because the double bond is in the middle. It's equidistant from either end of this molecule. So then we're going to add HCl to that. And then, yeah, no matter where, right? So if you think about it, so let me make some highlights here. So let's say our left or right carbon, right? No matter to which carbon you add chlorine, right? So you are going to have the same molecule as a result. So if, let's say, hypothetically, you encounter the question, which substrate will be best, right? So let's say like 2-hexene or 3-hexene. Then you can unambiguously say that, okay, well, looks like after our analysis, which we have conducted so far, so the 3-hexene will be a better candidate. So because we are going to obtain only one potential product, right? Not like two possible products, which will be like hard to separate because they're very similar to one another. Then it's going to be very hard to kind of like pull them apart, so to say, right? So that's it. So that's going to be our one and only product that we're going one and only product that we're going to obtain as a result of this hydrohalogenation reaction, in which HCl will be reacting with the 3-hexene. So at this point, that's it. So I hope that you have enough food for thought for your future like considerations when you tackle various problems. And at this point, have a good afternoon and stay focused, productive, and strive. Bye, everyone.